to have these points. Particles do not collide with the walls of the container because the particles are in a lattice. Particles are fixed, they only vibrate, therefore it doesn't take the shape of the container. So if you've said that particles don't collide with the walls and that they're in a fixed position in a lattice, then you would get the majority of full marks for that, if it was like a test question. For liquids, particles are disordered and mobile. Particles collide with the walls of the container, and for the volume, they collide with the walls of the container for the volume that it occupies, and therefore liquids take the shape of the container with constant volume. So if you said that particles are disordered and mobile and they collide with the walls of the container, you'd get for most of the marks. And also if you said that it has constant volume, you'd get like 100% of the marks. So yeah, you'd probably want to mention that it has constant volume if you haven't already. For gases, again, particles are disordered and it fills the entire volume of the container. Particles move until they hit the walls of the container. Therefore, gases take the shape of the container and expand. Again, you need all of those dot points to get full marks for that question if it was an adjust. Are there any questions for that? Does anyone want me to explain anything more? Okay. Okay, does everyone have their data booklets? Yeah. I have a spare one. Do you have?
No.
Okay, cool. Okay, if you could go to the periodic table.
Oh, wait, sorry, Nemo.
Yeah, that's okay.
Thank you.
No worries. You need a periodic table. Did you need one?
No, yeah, I need one.
Sorry.
I didn't see it.
No worries. You go to the periodic table and look for carbon in the periodic table. Okay, and look at the number on the top and the number on the bottom. Like this is just to refresh from last week or however long ago we did the first lesson. But the number on the top, it has the atomic number, and the number on the bottom, it has the mass number. But we know in conventional notation that you put the mass number at the top and the atomic number at the bottom. Is that understood? Okay. Well, I should have said that before going through the last question of the homework, but that's okay. I just wanted to throw it in there anyway. Okay. If we could go to page 3 of the notes, we'll take a look at the table and those two tables. Yeah. For because the first table was originally homework, but I do get last week anyway. Okay, so for mass number, mass number is for the first one 1, for the second one 2, and for the third one 3. The atomic number remains the same as 1 for all 3 isotopes. The number of protons is the same as the atomic number, and again is 1 for all 3. The number of electrons is 1 as well, because the number of protons will equal the number of electrons. Hey George. Good morning. We're just going to do the homework from lesson 1. Okay. So we're just on page 3. So, and the number of neutrons for the first one is 0, and for the second isotope it's 1, and for the third isotope it's 2. Did anyone get all of that? I mean, did everyone get all of those, or do I need to go through it again. Have a good milky and cool. Okay. So for the table below on page 3, we'll go through the similarities and differences. So can anyone give me a similarity between two isotopes of a given element?
Same number of electrons.
Yes, very good. If you've got that, give yourself a tick. He's already done this class.
Actually, they didn't give us this part.
We didn't.
We didn't do the problem.
Oh, that's so weird. Okay, well then it'll be a learning experience for you as well. Again, I was wondering why it wasn't open. That's so weird. Okay. Yeah, number of electrons is 1. Can anyone give me another similarity between two isotopes of a given element? Yes, very good. Number of protons is another one. Now, this will be the one that people may not get, so this is a tricky one, but can anyone think of any other similarity between two isotopes of a given element, other than the number of protons and number of electrons?
Is it the same things?
Yeah, sorry. But it's very similar to that, right? Yeah. But yeah, yes, but that kind of falls under the same as number of protons. But very good. It's the same chemical properties, so they would have the same chemical properties of one another, because all that changes is the number of neutrons. And yes, since they have the same number of electrons, they would behave similarly to other isotopes of the same kind of element. Okay, can anyone give me the differences, or one difference between two isotopes? Very good. And another one? Milky?
Neutrons.
Yes, number of neutrons is another difference. And again, this is one that maybe wouldn't get, but what's another difference between two isotopes of a given element?
Is it reactivity?
Yes, it is. Since chemical properties is kind of reactivity as well, but if I said chemical properties for similarities, so another one that's like the opposite almost? Yes, yeah, you're right. So they have different physical properties and different nuclear stability. So different physical properties and different nuclear stability. Cool. Okay, now everyone put their periodic tables away, and notes away, because I'm going to give you a mini test. So for this one, do you want to do this one? So for this one, you have 6 minutes. Make sure to write your names. Please. And you can start. Also, for like the last question or the second last question, you can write your answer over the page. You have 2 minutes left. You have 1 minute left. Do you have your name on it? Do you have to hear the next week? Cool. So, we're going to be talking about electrons today. So, right. We know that in an atom there are protons, neutrons, and electrons. But, and we know that both protons and neutrons are located in the nucleus, and where electrons are found are outside the nucleus, orbiting the nucleus. I'm sure you may know this already, but we're going to start here. Chemists found out that they're not just randomly rotating around the nucleus, as you may have seen in like those symbols of like electrons just kind of looks cool though. Like that picture, surely you've seen it. They're actually rotating around the nucleus in specifically defined energy levels called shells. And they range from very close to the nucleus to very far away. When the electrons are closer to the nucleus, they have a stronger attraction to the nucleus. And you can imagine that when two opposing charges are very close to each other, it'll be very hard to take away from one another. And what this results in is the electron is very stable. So when the electrons are closer to the nucleus, they have a lower energy and they're very stable. But as you go further and further away from the nucleus, the electrons become unstable. And as a result, they have a higher energy. So does that make sense so far? The closer the electrons are to the nucleus, the more stable they are, and as a result have a lower energy. And the further the electrons are away from the nucleus, the more unstable they become and have a higher energy. Is that clear? Cool. So, how did we figure out that they're in defined levels and arranged into shells? Well, a scientist got hydrogen. I can't remember which scientist, but he got hydrogen. It has one proton and one electron. It's literally one proton and one electron orbiting around the proton. And he added energy into this system and then saw that the electron jumped into a higher energy level. Okay, let's just say these are other shells. But it didn't stay in this higher energy level for long. It then, over time, returned to that energy level and then again back to where it started. Okay? And then each time it returned to a lower energy level, it released some energy, and this is called emission. I don't think it has two names. The emission. Okay? And believe it or not, you've probably seen this in real life. Can anyone guess where, except George? Okay. You can see it in a firework. When the electrons of whatever metal that is inside the explosive explodes, it results in all of the electrons in that being excited and then emitting colors. And depending on what metal you load into the firework, it'll show a variety of different colors when it explodes.
It's purple.
I can't remember all. I'm pretty sure like sodium's green, I think. Copper is orange.
Strong things, right?
So all of the different metals have a different color when they emit after electrons being excited. I think we might be doing, not us, but I think you might have done an experiment like this in high school where you had like the Bunsen burner with the wide flame and you sprayed some stuff into it. Yeah, that was fun. I remember that. The electron absorbs that given energy and then releases. So what I should have said before is that, do you think there are other shells in the hydrogen atom because it only has one electron? You might think that there isn't, but there are. And the way that this was proved was by actually adding energy into that electron, and then it jumps to higher elevated energy levels. So, despite some atoms not having those energy levels occupied, they do exist. And it was proven by the scientists who added energy into that electron to get it into those higher energy levels. Does that make sense? Okay, cool. So, the name of the scientist was Niels Bohr, by the way. Then, he added a massive amount of energy to that hydrogen electron, to see, to the highest extent. And then, as he was, as the electron was returning to the first energy level, also, the first energy level is known as the ground state. Okay, that's the term that we use for the lowest energy level. It's the ground state. And anything higher than the ground state is an excited state electron. Okay. And as it returned, he noted the colors that were being emitted as the electron was returning to the ground state. And he plotted that on a graph, and this is known as the hydrogen emission spectra. And if you turn to page 4, you can see the hydrogen emission spectra, although it's in black and white. But those wavelengths are the wavelengths at which the hydrogen atom emitted colors. Okay, and that's known as a spectrum. So, yeah. He tried again with other different forms of energy, electrical energy, heat, and every time when the electron was excited, it would produce the exact same spectrum. Okay. So, yeah, maybe I'll write it on the board. You don't need to copy this down or anything. It's already in the notes. The lowest energy state is the ground state. And anything higher is excited. Okay. Are there any questions from what I've just explained? Good. The human eye can detect between red to violet in the spectrum. So anywhere beyond those two colors is known as infrared and ultraviolet. And despite us not being able to see beyond those, beyond violet or below red, atoms will still emit light of that wavelength. So even though we can't ourselves detect those emission, it'll still happen. And there are various detectors that you can use to see what wavelengths at which an atom being excited emits wavelengths. So, yes. When we move further, so let's just recap about what we learned just before. When you move further away from the nucleus, it becomes shade. The electron becomes
as high energy.
Yes, and as a result,
Is in excited state. Moves into high shell.
yes. Not what I'm looking for. Does anyone know kind of what I'm looking for? If I said, okay, let's start from the lower energy. If it's closer to the nucleus,
That's
it'll-
more stable.
yes, that's right. And if it's further away,
Okay.
yes. Sorry, that's okay. It's okay. That's what I was looking for. So yeah, that's what we explained earlier. Closer it is to the nucleus, the more stable it is. And further away from the nucleus, the more unstable it is because it has a higher energy. Okay, with this close. That's okay. Cool. Have a read of the first section. Sorry. Up to here. And after that, we'll highlight that section. Okay, we'll start highlighting now because we've gone through that basically. So, from the heading electrons within an atom. Okay, arrangements of the electrons electron configuration. Responsible. Chemistry. Explain the properties, including the way react. Okay, now in the title of the next heading, shell model. Visible hydrogen spectrum consists 4 lines. Observed passing electric current. Now, with a pen, circle the word electric current. And annotate next to it, form of energy. Form of energy. Okay, continuing highlighting. Electrons, so the first dot line beneath that image, electrons moved around in specific energy levels, shells. Next dot line, electron, lowest energy, ground state. And annotate next to that, stable. Next to ground state, the word stable. Next up, right? Electron move from lower energy level to higher energy level. Now get your second highlighter color and then highlight the word transition. Continuing, in the regular color, sorry. High energy electron, excited state. And then annotating next to it. Does anyone want to take a guess? What we're gonna annotate?
Unstable.
Yes, unstable. Good. And the next dot point. Excited electron, unstable. Falls back to ground state. Emitting energy. Energy corresponds. Colored lines. Now in the graphic just below, if you could get one color and then highlight n equals 1, ground state. It's at the little table at the side. N equals 1 ground state. And then with the same color, highlight n equals 1 in the picture of the atom. And then again with a different color, highlight n equals 6 in both the atom and the table that shows the energy in the graph. So n equals 6 in both the graphic and the graph. can you go to page 5 of the notes? You may have done it in school already, but again, we're just starting from the beginning, so we're going to be going over it again. So, when you have electrons in shells, there's a specific arrangement to the electrons in each shell. The shell number is given as n, and the max for a shell is 2n squared. So, n, and the max of electrons for the given shell n is 2n squared. So if n equals 1, then the max number of electrons for shell number n is 2 times 1 squared, which is 2. And for shell 2, it's 2 times 2 squared, so 2 squared is 4, and 2 times 4 is 8. And if n equals 3, then 3 squared is 9, and 2 times 9 is 18. Okay? Alright. Now, shells also have within them subshells. And the way you know how many subshells there are in a given shell is as follows. So for shell number n, the number of subshells equals 10. Okay, what I mean is, for shell 1, there is one subshell. And, there is one subshell, and it is S. Okay. For shell 2, there are two subshells, S and P. For shell 3, there are 3, S, P, and D. And for shell 4, there are 4, S, P, D, and F. For our syllabus, we won't be going probably anywhere near shell 4 when we're writing subshell notation. But if you're asked about it, how many subshells does shell 4 have and what are they, then it's SPD. It's a bit of, it's just a number. What subshells there are. In addition to subshells, there are also orbitals. In hindsight, I wish I drew it a bit further away, but I'll draw them here. So maybe I'll label it as well. So these are shells, and the max number of electrons. These are subshells. And then within subshells, there are orbitals. Okay? So, for orbitals, we know that they go into subshells. So, we'll write out the different subshells first. And the way you remember the number of orbitals within a subshell is 1, 3, 5, 7. Like the odd numbers. Yes. So there's 1 orbital in subshell S, 3 in P, 5 in D, and 7 in F. And then the number of electrons in each orbital is just 2 times that number, because each orbital can accommodate a maximum of 2 electrons. So in subshell S, there are 2 electrons. In subshell P, there are 6 electrons. In subshell D, there are 10 electrons. And in subshell F, there are 14 electrons. Okay. That may have been a lot to take in. Are there any questions at all about what I've just said? Any at all? It's fine if you get confused. Yeah? Okay. Okay. Alright. So, in school, you may have already done some shell level electron configuration. And you've probably been told that the max number of electrons in a shell is 8. Is that the case? Maybe? I don't know in science, but it was a long time ago for me. But anyway, so if you're writing the shell level electron configuration, for an atom with 11 electrons. Does anyone want to look that up in the periodic table? I can't remember it.
Sodium.
Yes. Cool. With 11 electrons, you would be writing 2, 8, 1. Does that look familiar? Yeah, probably. So, that's the way you may have learned it at school, but the way you are expected to write it in year 11 and 12 is using the subshell notation. So that is taking into account the subshells and more or less the orbitals as well. So you'd first write the first shell, and then you'd write the first subshell, and then you'd write, well, since we're filling in the max number of electrons that goes into that subshell, and we know that that is 2. And then you continue. We know that first shell only has one subshell, which is S. Then we go to the next subshell, the next shell. And then again we start from the lowest energy subshell, which is S. Again, fill it in. Then move on to the next subshell. Do you see how it's going? And then when you fill the max number of electrons for that subshell, which is 6, because it has 3 orbitals. And then you would like take a minute to count how many electrons you filled in so far. So there's 2 plus 2 is 4, and then plus 6 is 10. You still have one more electron to fill in. We've already reached the max number for shell 2. And then we move on to shell 3, first subshell, and then so that is how you fill in the electron configuration for subshell notation. Okay, it doesn't stay that simple, and even if you probably don't find that simple at all, but with a lot of practice, it gets really easy. George can tell you how easy it is. How easy is it, George? Yes, very, very easy. Yes. So, we'll take another example. So, for atomic number 19, anyone tell me what atomic number 19 is? Yes, potassium. So, this was sodium, and 11 electrons. No, that's probably very terrible to write it like that, because reasons. So, sodium has 11 electrons, and potassium has 19. So, instead of doing the shell level, we'll go straight to the subshell level configuration for sodium. That has 19 electrons. Again, we start off by filling up the first subshell, and the next, and we keep going. And then, so we've reached basically where we finished up last time, so we know that there's 10 for there, and then we still have another 9 more to fill. And you start off with, here's 2. Now, a peculiar thing happens here, because I'll explain. I'll show you what happens first. Instead of filling in the D subshell, we skip to the 4S subshell. Now, the reason for that is, and this is where it gets a little bit confusing, but hold on with me for 1 minute. The reason for this happening is, in the atom, as you get further away from the nucleus, I tried really hard to show it, but in case you can't see what I'm trying to do, as you get further away from the nucleus, the shells get closer and closer together. You may not be able to see it, but yeah, they get closer and closer together. But what has happened here is that the third shell and the fourth shell, like get a magnifying glass, have like come so close that they've overlapped. In fact, so some of the subshells of, well, literally only the S subshell has overlapped with the D subshell of the third shell, and what that means is it fills before 3D. And the reason for that is that when you're filling electrons in an electron configuration, you fill from the lowest energy to the highest energy. And since 4s is a lower energy than 3D, it fills prior to 3D. Does that make sense? Okay. Cool. Now, there is a rule that I will tell you that you can apply for any situation with regards to what fills first, and yep. So and that is that it only occurs with the S and D subshells of like the third and fourth, and the fourth and fifth, and the fifth and beyond that. But like you wouldn't be asked to go much beyond what was it, 30 electrons. So I think that's what I said. But yeah, it's like in year 11 syllabus, and even year 12, you wouldn't be asked to do the electron configuration for an outrageous number of electrons, so you don't have to be worried. So if you want to make a generalization for this phenomenon, the generalization is that the energy of shell n plus 1 for subshell S is, yes, less than the energy for n of subshell D. Okay, so if we apply to this example, if you're looking at shell 3, 3 plus 1 is 4. 4s is less than 3d. Now, you can imagine that this only applies for shells that have a d subshell. So, if we go back to the subshells, only 3 and beyond have a d subshell. So, you can't like say, but what about shell 1? How about 2s is less than 3d? Well, it is, because like it's all the way here and 3D is like all the way here. I guess it works there as well. But okay, it does work. Cool. That's a generalization. Does that make sense? Any questions at all? Okay. Awesome. Alright. There is one more thing that I wanted to show. I wanted to say there's one final rule. Regardless, the valence shell, I don't know if I explained it before, but the valence shell is the outermost shell that you have in an atom. It never has more than 8 electrons. You may have heard that in school as well, but that's called the octet rule. And it doesn't happen, but when you have 8 electrons in the valence shell, it is the most stable. And noble gases have 8 electrons in the valence shell. Yeah, regardless of the number of electrons. You can have, even if it had like 100 or something, you'll only have less than 8 electrons or 8 electrons in the outer shell. Okay. The next thing I wanted to talk about, space. The next thing I wanted to talk about is orbital filling. So, if you were asked by the examiner to show how orbitals are filled, I really doubt this would happen, but it has happened. This is how you would do it. So, for the first shell, it has one orbital. And the way you denote what an orbital looks like is by drawing a box. This is the 1s orbital, and it has 2 electrons in it. And the way you fill this orbital with 2 electrons is by drawing 1 arrow going up and 1 arrow going down. That is a completely filled 1s orbital. Now, if you are asked to draw if you're asked to fill in the orbitals for p, now you draw the number of orbitals p has, which is 3, it's 1, 3, 5, 7. And you know that it has a max number of 6 electrons. If it had, say, if it had 4 electrons in your p subshell, say you had or 8 electrons in your 8 atomic number 8. It's oxygen. Say it oxygen, and then its subshell configuration is 1s2, 2s2, 2p4. So if you had that and you had 4 electrons in your p subshell, and you were asked to show what the orbitals for the p subshell would be filled in like, you may be tempted to draw this. But that is in fact wrong. This is not how you fill in orbitals. I don't know why I did that, because I was going to write it anyway. But the way you actually fill in the p, or any orbital for that matter, the way you fill in orbitals is by half filling them first, and then coming back to completely fill them. And the way this happens, the reason why this happens is to minimize repulsion between electrons. In the before case, you had 2 orbitals with 2 electrons in each orbital, and when they're, so the way it looks, it's kind of as you're going around the atom. So when you have 2 orbitals that both have 2 electrons in it, you would have 2 electrons that are close to each other and repelling one another. But when you're filling half, in most scenarios, you would have 2 or many orbitals that are half filled, which is much better, or better. And well, the best is when it's completely filled, but yeah, you just remember that you half fill before you completely fill. Does that make sense? All right. Okay. Okay, so get your exercise book and put the heading electron configuration of atoms. Sorry, I just need this as well. No, I forgot to write this on the board before. I might use yours. Thank you for coming. And copy down the shells, subshells, and orbitals as I've done there. Probably a bit better than what I've done, make it more legible. Has everyone finished writing shells? Okay, so I can rub it out. That's cool. Can you finish writing shells? Can you grab this? So this is another example that I wanted you to copy down, but I misplaced or erased the board that I had, like a whiteboard like that, left to make room for homework. And so, fortunately, George came, and he's got it written down. So this is just an example to show how the orbitals are filled in. And after you copy this down, can you leave a gap of around 4 lines, and then I have another example after. Okay, so if you would start copying that example.
think I can't remember, but there's a certain combination of subshells where usually the line would be full on behalf of the concept,
Yes.
it's half filled.
Yeah, so that's cobalt and chromium
Yeah.
and magnesium. But if you want, I can tell you the counterparts. Or actually, yeah, so that's where it is.
Yeah, I think it's white and that's
But I might actually, if there is, because I actually like this one. I just looked off my mouse scrolls. Does everyone copy that down? Or go through? Okay. Yeah. So again, just leave 3 to 4 lines of space between example 1 and 2. Thanks. And again, sorry I didn't have this already before. Let's look that one.
all the homeworks and stuff.
Yeah. No, I've seen you. Good student, George. Okay. In the gap that I asked you to leave between the 2 examples, I am going to dictate 2 dot points that I want you to write there. The first dot point is electrons have a negative charge. Therefore, they repel each other. In an orbital. So again, electrons have a negative charge, therefore they repel each other in an orbital. And the next dot point is to minimize repulsion, subshells first half fill, then fill completely. To minimize repulsion, subshells first half fill, then fill completely. Okay. Now take up page 5 and 6, and we'll start highlighting that. Oh yeah, the other thing is at the end of the lesson, if you want to take a photo of the homework for this lesson, feel free to do so. And yeah, and then also I'll give you the homework for our next lesson.
Is it the same as?
Yes, yeah. So from the third dot point, same shell highlighting. Same shell. Same distance from the nucleus. So third dot line on page 5, same shell. And then same distance from the nucleus. And then same energy. Then annotate next to same distance from the nucleus. Therefore, shells are circular. Therefore, shells are circular. And then, next to same energy, when electrons move around the nucleus, no spectrum is observed. So that's why you don't just see sodium magically light up green by itself, just existing. So only when you put energy into it does it. Next up, point. Electron close to the nucleus, attracted more strongly than further away. Further an electron from the nucleus, next up line. Further an electron from the nucleus, smaller energy required to remove it. And the reason for this is that it's more unstable, so therefore it's easier to remove than one that is more stable and more strongly attracted to the nucleus, which would be closer to the nucleus. So again, it kind of makes sense when it's further away from the nucleus, it's easier to remove. Anyway, next up line, different shells. Hold different numbers of electrons. Now get a different highlighter color and highlight shell number, in the table, shell number, max number of electrons, and in the bottom row n and 2n squared. And then right next to it, max number of electrons per shell. Max number of electrons per shell. Okay. Now for the first dot point, I want you to stay in the same different color. I mean the first dot point after the table. To stay in the same different color and highlight outermost shell never contain more than 8 electrons, regardless maximum possible number for that shell. So even though shell 3 can hold 18 electrons, if that is its valence shell, well, it won't have 18 electrons. You'll be able to see as you're filling in subshell notation that you'll never end up with more than 8 electrons in your valence shell. And then annotate next to that last dot point, that second last dot point, the octet rule. So after what you just highlighted, the octet rule. Octet is spelled O-C-T-E-T. Okay, and then now returning back to your regular highlighter color for the last point. Electrons, outermost shell, called valence electrons. Valence electrons involved in chemical reactions. And that's the reason why the noble gases are very stable and unreactive, is because they complete their valence shell according to the octet rule. And when the valence shell is incomplete, that's when they get relatively unstable with respect to noble gases, and those are the ones that partake in chemical reactions. Okay, over the page to page 6. So under subshells, the first outline, within shells, number of subshells in each cell equal shell number. Labels spitted. Energies, each shell, order SPDF. So that's just showing that what energy levels. S is the lowest. Contain orbitals, all have the same energy. Now, skipping the table and going to the next dot point, gives number of electrons in any orbital. And then with a different highlighter color, highlight an atomic orbital called maximum 2 electrons. So that's known as the Pauli principle, just how many that orbitals can hold 2 electrons, and there are 1, 3, 5, and 7 orbitals in each subshell. That's just known as the Pauli principle, after the person who discovered it. Okay. Moving on to the next point, back to the first highlighter color. Order of filling the subshells in the heading. Electrons occupy lowest energy subshell first. As shells move away from nucleus, closer to each other. Some cases, subshell 1 shell, higher energy, that subshell next shell. And then double underline the word next shell, the words next shell. Sorry, and then returning to highlight the last point, order of subshells energies. Order of subshell energies. Now, if you could write, do you know that bracket sort of thing? If you could write that above 4s2 and 3d10. And then also at the end of after 5s2, also write another symbol like that in 4d10. And then put a curly bracket on top of 5s2 and 4d10 also. And then at the little gap between, right? One S is less than energy of mg. Also, one other thing that I forgot to mention before is at the end, underneath and next to what you underlined, double underlined, next shell, write in brackets EG, 4S, and 3D. So just next to that, next one. EG, 4S, and 3D. And I think we'll go through, so is everyone, yeah, of course, we've already copied this now. So for a bit longer, we'll go through some examples of writing electron configuration, just to consolidate what you've learned. Also, are there any questions at all about what we've done so far? Any questions at all about what we've done so far? No? Okay. I will give one example, or some examples of electron configuration, and we'll go through it together. And then maybe after that we'll give you some examples to try, and we'll correct ourselves. So. Okay, let's start off with easy. Go through, actually, I'll do a hard one, and then we'll give you an easy one. So, okay. Let's do magnesium. Magnesium has 12 electrons in its configuration. So the way we would write the subshell notation electron configuration for magnesium is we start off with the lowest energy levels, and we go -2, it's already filled, 2, -2, and we know that subshell 2 has, the shell 2 has 2 subshells, S and B. Then move on to the next subshell, 2B6, and we kind of stop and think how many electrons that are filled in so far. It has 12, we've done 10 so far, so then we move on to the next shell, because we've already completed shell 2, and then fill in the rest. So 1 is 2, 2 is 2, 2b6, 3 is 2. If you have, yeah, you can copy this down. So this is just for like practice, and some of the homework questions ask you to write the subshell configuration anyway, but it's just get a bit consolidating our knowledge. Okay, okay. Now I'll get you to try to attempt the next one on your own, and then I will correct you afterwards. So fluorine. Here we go. Result. Fluorine, the electron configuration. Now I've already given you that it has 9 electrons. Okay, has everyone had a good? Alright, you've got this, you are correct. Give yourself a tick. Good job. I'm pretty sure everyone got it right. Well done, everyone. Okay, let's go for a harder example, maybe one that incorporates that rule we learned about how forest fills before 3D. So let's try calcium. Fairly sure. Yeah. Example 3. Calcium. I don't expect everyone to get this right on the first go. I had a lot of trouble, not a lot of trouble, but I had a bit of trouble, some trouble, when I was learning this for the first time myself. And it's okay, because the more practice you get, it becomes like super easy, like 1 + 1 sort of thing. You'd be happy to see this sort of question on the test. You'd be like, oh yes, electron configuration, I can do that, easy marks. Okay, has everyone had a go at writing the electron configuration for calcium? Okay, cool. So, we start with first shell. Pretty simple so far. It's 10. It's 18. Now we've reached 3p6 and we filled it in. And we know before filling 3D, we have to fill for us. So we fill it in. It's 10, that's another 10. It's 20. You got that? Well done. You are, oh god. Okay, okay, let's try another one, maybe one that incorporates 3D as well. So let's try manganese. That's a good one, so that's 25. As I said, the more practice you get with this, the easier it becomes. Everyone finished? Cool. Here's the answer. S2, 2S2, 2P6, 3S2, 3P6. Again, we're up to 3P6, so we have to check. Yep. 4S2 fills before 3P. 4S2. Now that we filled it, we're allowed to move on to filling in 3D. We count up the number of electrons, it's 20, and we have a possible 10 electrons in 3D, so we fill in 3D 5. Anyone get that?
Yeah, I got it, but like, why is it 3D? So why is it 3D 5?
Okay. The reason that, sorry, is your question that you don't know why it's 3D 5?
Yeah, but why is it 3? Why isn't it like 5D 5 or something?
Right, because we still haven't completely filled the 3D subshell, and we know that 4s2 fills before 3D because of that rule. So e n plus 1 s is less than e of nv. So we know that 4s fills before 3D, and once we've filled 4s, we need to completely fill the third shell before moving on to the rest of the fourth shell. So let's just say, for example, that 3D10 was completely filled, and then after you fill the 3D10, you'd continue to start filling in the rest of shell 4. Does that make sense? So you completely fill each shell, and I mean, like, if this didn't exist, you, for example's sake, it's actually not the case, but you'd fill in like 3 before moving on to 4, and so on. But since 4s has lower energy than 3D, you have the 4s in there. Okay. Are there any other questions? Is that clear with that? Cool. Alright. Now I'll give you the homework for next week's class. I think there'll be a lot more people coming next week, so I'm going to be splitting it up into 2 classes. I will let you know what time I'd like you to come. For the moment, take a photo of oh yeah. Okay, no worries. I don't think it's available in the shop yet, and this is just a preview version that some schools got somehow, I don't know. And like the real one's much thicker than this.
Okay. Yeah. I didn't pay for the one I had, so I should
I think it's $80 from memory.
But
No, I'll go through that after I discuss some things. The rest for next week. Okay. Has everyone taken a photo of the homework? You can come closer if you like if you couldn't get a clear photo, that's fine. Okay. Alright. Shane, you're planning to come at 11, right?
Yeah.
Okay. Because that's when I got you for like regular classes, like 11 o'clock.
Yeah.
And you can continue coming at 9. And Milky, you said you were moved to 9 AM because you have other commitments, that's fine. 9 o'clock is good. Nethly? Cool. Sorry, I've like got a massive list of names and it's difficult. Are you alright to come at 11 o'clock?
Yeah.
Okay, cool. Yeah. Also, one more thing, I'd like to keep this. So, I'm sorry that you took it home last week.
Yeah.
And by the time I realized it was too late. Awesome. So Shane and Bethany coming at 11, and Kyle and Milky coming in at 9. George and Shane Yeah, so I don't know if my mom told Milky and Anthony, but like signature and paid or not paid, and the reason for that is so that if you don't have the chance to pay this week, you can pay next week or the week after. It's fine, just as long as I know, and it's an easy way to keep track. Excellent.
My dad has the money in the
Yeah.
account.
Yeah, you can write those numbers there if you want.
Did you have to?
Yeah.
Like,
That's 10 for you. That's 20 for you. And I don't need you to sign the signature. But, yeah. If anyone's curious, George has already done this lesson and every lesson, and I invited him if he wants to come do this second time for revision. So you can find a copy of this online. You just type in PC data chemistry, and like it'll probably be the first link. It's probably a PDF. But if you can't, just let me know. For the people who don't know, my number is 045 222 8230. And if you have any problems, you can give me a call, and I will try my best to help you. Or like if you can't make the class, or if you want to go to a different class, because like I only have 9 o'clock and 11 o'clock, but if you want to come in at 11 instead of 9, or 9 instead of 11, you can let me know, and then I'll be able to shift you. Okay, thanks for coming. I'll see you next week.